have to spin on the opposite direction. So this is the summary of the relationship of quantum numbers. Principal quantum number n, the angular momentum quantum number L, the magnetic quantum number ML, the number of orbitals that we can have here. Now this is a table from another textbook there, and I don't believe you have a similar table in your textbook, in the current textbook there, but I think this is a better summary there. Okay, so look at the relationship again. N equals to 1, that's the principal quantum number. You can only have one value for L, L equal to 0. And when L equal to 0, you can only have one value for ML, ML equal to 0. And when ML equal to 0, that means there is only one orbital. There's only one room in this hotel. That's the 1s orbital. Okay. Now when n equals to 2, there are two values, two possible values for ML, 0 and 1. If L equal to 0, then ML equals to 0, representing the 2s orbital. If L equal to 1, ML could be positive 1, negative 1, 0. Three possibilities there. There are three rooms in here. So that's the three 2p orbitals. So s orbital, one room. P orbital or p sublevel, you have three rooms there. The total orbital in here in n equals to 2 though, 3 plus 1, 4. Okay. There's 1 on n equals to 1. There are 4 on n equals to 2. There are a total of 9 orbitals on n equals to 3. Where do we have those 9 orbitals there? Well, when n equals to 3, three possibilities of L, 0, 1, and 2. 0, 0, 1 orbital. 1, 3 orbitals. 2, 5 orbitals. These are the room numbers that we use to identify the orbital. So negative 2, negative 1, positive 0, positive 1, positive 2. Those are the 5 orbitals. Okay, and you have 5 3d orbital, you have 3 3p orbital, you have 1 3s orbital, adds up to a total of 9 orbitals there. And then if n equals to 4, these are the possible values. So what I need you to do here is then take a look at this table carefully and try to understand the relationship among the first three quantum numbers. And we don't need to worry about the ms. Well, ms, well, that's the number that we use to differentiate between the two electrons already identified, and the exact location of those two electrons already identified. We use positive 1 of 2, negative 1 of 2 to differentiate those two electrons there. What I need you to understand is the relationship among the first three quantum numbers, n, l, ml, and what do they stand for. Okay, so this particular table is very important for us to determine where the electron is, or the exact location of that particular electron, or what is the postal address for that particular electron. So we need you to know your quantum number, understand the relationship among different quantum numbers there. And since m is pi, I do want you to take a look at these examples for practice on page 317 and 318. I have them on here. So this is an example of the question, the textbook I'm asking you. What are the quantum numbers and names of the orbital in n equals to 4 principal level? And how many n equals to 4 orbitals exist? Well, you need to go back to that table that we showed you, summarizing the relationship. So in this case, when you try to approach this question, we're basically trying to assign postal address to different electrons there. So we know n equals to 4. So the principal quantum number, n is 4. L, you should be able to predict. When n equals to 4, there are 4 possible values for L. Namely, starting with 0, 1, 2, 3. Now, ML, this stands for the orbitals there. Okay. When L equal to 0, ML can only be 0. When L equal to 1, ML could be negative 1, L plus 1, 0, positive 1. When L equal to 2, ML would be negative 2, negative 1, 0, positive 1, positive 2. When L equal to 3,
Negative 3.
negative 3, negative 2, negative 1, 0, 1, 2, 3. Okay? So that's what happens when you're given n equals to 4. The possible L values and M out values are identified. If you know the M value, you should know all the possible L values and M out values. So if n equals to 1, L can only be 0 because 1 minus 1 is 0. And then ML can only be 0. There is only one orbital when n equals 1. When n equals to 2, well, L could be 0, L could be 1. When L equal to 1, you have negative 1, positive 1, 0. 3 possibilities, 3 orbitals there. When L equal to 2, 5 possibilities. Okay, so the total number of orbitals here we have 1, 3, 5, 7. And you can predict when L equal to 4, how many orbitals do we have here? 9, 11, 13. It's always an odd number. 1, 3, 5, 7, 9, and so on and so forth. So that's a relationship there. And when we try to solve this kind of question there, first we want to determine the possible values of L from the given n equals 4. So if n equals to 4, these are the possible values for L. Okay, so and then when you have n equals to when L equals to when the possibility of L is identified as 0, 1, 2, and 3, then the possibilities for ML is also identified based on the relationship of that 2L plus 1 possibility. Okay, so in this case, and we determine the possible values for ML. Once we determine the possible values for ML, then you can determine the total number, because the number of ML values is equals to the number of orbitals there. So here you only have 1, 0. Here you have 3. Okay, here you have 5. And here you have 7, and so on and so forth. Okay, so the question also asks you how many n equals to 4, how many orbitals have the value of n equals to 4? Well, you just add all the numbers together. 7 plus 3 is 10, 10 plus 5 plus 1, total of 16. And 16 equals to n to the second power. That's another relationship I need you to memorize. When you are given an n value, n to the second power is the total number of orbitals. So when you go to a hotel, and the first hotel, n equals to 1, 1 to the second, there is only one room in that hotel. When you go to the next hotel, n equals to 2, 2 to the second power, there are 4 rooms in there. When you go to the next hotel, n equals to 3, 3 to the second power, 9. There are 9 rooms in that hotel. Okay, so the higher the n value, the more orbitals that we have. The more orbitals we have, the more electrons we can accommodate. The relationship between the number of orbitals and the n value, n to the second power. Later on in the next chapter there, we'll say the total number of electrons that we can accommodate at each main level is 2 times n